You know, every single day you pick up and use things that have been carved with just incredible precision. Your phone, your car, you name it. But behind every single one of them is this invisible force. It's the one thing that decides if a part is absolutely perfect or just a useless piece of scrap. Today, we're going to pull back the curtain and make that force visible.
I mean, really think about it for a second. That sleek metal case on your smartphone or those unbelievably complex parts inside a jet engine. They don't just, pop into existence. They are literally sculpted out of solid blocks of metal. So what is it? What is that fundamental, hidden force that lets us shape our entire world with such mind-blowing accuracy?
Well, it's called cutting force, and it's exactly what it sounds like. It's the raw physical pushback a material gives when a tool tries to cut and shape it. And let me tell you, trying to master this force, that's one of the biggest challenges in all of manufacturing. It is the razor's edge between success and total failure.
Okay, so let's break it down. What is it really? At its heart, it's the force the cutting tool puts on the material. Sounds simple, right? Well, no. Controlling it is anything but simple. If you have too much force, snap, the tool breaks. Too little, and the cut is all wrong. So, being able to predict this force is absolutely crucial for everything, from how long your tools last to the final quality of the surface. Get it right, you've got perfection. Get it wrong, well, it's game over.
So how in the world did we first start to even understand, let alone predict, this incredibly important force? Well, it all started not with supercomputers, but with the fundamental laws of physics, sketched out with a pencil right on a piece of paper.
The original way of thinking was based on something called shear force models. The basic idea is that when you cut something, the material deforms and breaks along this tiny, tiny line called a shear zone. Early theories were all about creating these mathematical blueprints to calculate the forces happening right in that zone. Over time, of course, they got way more detailed, adding in other factors like friction, and this method is still evolving. For instance, a 2022 study by Huang's team made these models even more on point by figuring out how that shear zone acts in more dynamic, non-uniform ways. It just goes to show how sophisticated even these foundational ideas have become.
But, paper and pencils can only take you so far. The next great leap forward was to take this whole physical process and build a perfect digital twin of it, a complete simulation running inside a computer.
And this brings us to what's known as finite element analysis, or FEA. Think of it like this. The classic shear force model we just talked about, that's the mathematical blueprint. It gives you the final calculations. But FEA? Oh, FEA is like a hyper-realistic video game of the entire cutting process. It doesn't just calculate one thing, it simulates the whole event. It shows you the forces, the temperature changes, the stress deep inside the material, and even how that little metal chip curls away. It's a complete virtual testing ground.
And that is the absolute key. FEA lets engineers visualize things that are just physically impossible to see in the real world, especially during the chaos of a high-speed cutting operation.
So, just how powerful is this? Well, research in 2025 from Pasternak's team gives us an awesome example. They used FEA to simulate what would happen if you preheated a super tough titanium alloy right before cutting it. The simulation predicted a staggering, and I mean staggering, 60% reduction in cutting force, all because the heat softened the material. This wasn't some wild guess. It was a validated discovery made possible because they could see the invisible physics at play right there on the screen. And it goes so far beyond just force. FEA can predict pretty much everything, from hidden stress lurking under the surface to how the tool itself might bend or wear out over time. This is the kind of deep insight that lets us design parts that are lighter, stronger, and way more reliable, for everything from the most advanced aircraft to critical medical implants.
And that brings us to the modern era. What if instead of trying to program all the laws of physics into a computer, we could just show it tons and tons of real-world examples and let it learn all the patterns for itself? Well, welcome to the world of AI and machine learning.
This is a complete paradigm shift, a totally different way of thinking. Physics-based models like FEA, you have to feed them all the material properties to solve complex equations. They're fantastic at explaining why something happens. But data-driven AI models, they're different. They learn directly from sensor data, force, vibration, even sound, to spot incredibly subtle patterns. They are amazingly accurate at predicting what is going to happen, even if they can't always explain the deep physics behind it.
And there isn't just one type of AI that does this. Researchers are building a whole new toolkit of AI specialists. For example, they're using LSTM networks. That's a type of AI that's great at understanding sequences over time to predict exactly how a tool will slowly wear down. Others are using CNNs, the same kind of AI that powers image recognition, to analyze data from tiny sensors that are embedded right inside the cutting tool itself. It's all about picking the right AI for the right predictive job.
So, okay, we have physics on paper, we have this incredible virtual simulations, and now we have these AI-powered crystal balls. So which one is the best? Well, the future isn't about choosing just one. It's about combining all of them into the ultimate toolkit.
The most powerful and exciting new approaches are all hybrid. For instance, a 2024 study by Reber and his colleagues took the incredibly detailed data that was generated by an FEA simulation and used it to train a machine learning model. And the result? They achieved over 91% prediction accuracy. They literally combined the deep physical understanding of a simulation with the insane pattern recognition power of AI. It's the best of both worlds.
Yeah, a key insight from the research really says it all. It's that combination. The hardcore numerical accuracy you get from simulations mixed with the incredible flexibility of machine learning, that's what opens up this powerful new frontier. That synergy right there is where the future of manufacturing is headed.
So this all leaves us with one final big thought. For centuries, manufacturing has always been limited by what we can physically test and measure. But now we can predict and optimize these unseeable forces that shape our world with almost perfect accuracy. So the question is no longer just how do we make things, but with this newfound power, what impossible things are we going to create next?